This is an overview video for College Trigonometry version 3 by Stitz and Ziegler. 10.2 The Unit Circle, Cosine and Sine. When you have a unit circle, so the radius is 1, centered around the origin, the points along the unit circle are identified by the x value called cosine theta. And it's shorthanded COS, cos. Cosine theta is the x value of a point along the unit circle, and sine theta is a y value. The theta represents the angle in standard position where the terminal side includes that point on the unit circle. For example, if we wanted to find cosine 270 degrees, the cosine is the x value, so we would first find our angle at 270 degrees, and that would put us a point right here. The x value is 0, so cosine of 270 would be the x value of this point of 0. Sine 270, same angle, same point, the sine is the y value. So sine of 270 would equal -1. They wanted us to find cosine of -pi. So in standard position, -pi is clockwise, pi radians around, which is a half a circle. So that puts us on this point on the edge. Cosine would be -1, sine would be 0. So cosine would be -1 and sine would be 0. Now these angles, 270, 180, 90, 360, these are called quadrantal angles, and they're pretty easy to spot and find the sine and cosine because they line up nicely on the intercepts. If we get into other angles, for example 45 degrees, it takes a little bit of geometry to find out the values of the point here. So if we took a look at this 45-degree angle, here we have the 45-degree angle, we do know that this length is 1. And from Pythagorean theorem, we could get that x squared plus y squared equals 1 squared. And the fact that x is the same as y comes from the fact that these angles are equivalent. They're 45, so the opposite sides would be the same as well. So then we could work with x squared plus x squared equals 1, and 2x squared equals 1, etc., etc. And finally we could find x, and then we could find y. A little bit more work to do on those. However, most students end up memorizing these, and they don't have to do this work other than maybe the first time. So another example, pi sixths. This is 30 degrees. How would we find the coordinates of the point at the end of the terminal side of this angle pi sixth, or 30 degrees? So here we have a pi sixth, 30 degrees. It turns out that this is a 30, 60, 90 triangle. And the key to finding this angle is to recognize if we made an equilateral triangle, this is 1, radius 1, this is 1, this is 1, that gets us that this piece right here would be 1/2, because the other 1/2 is down there. And so that way we can find the y value up is 1/2. So that would be the y value. And then the x value, you'd have to plug in to the Pythagorean theorem. Now that you've found the y value, you know that this squared plus this squared equals this squared, which is just 1, and you can find the x value. That ends up being the square root of 3 over 2. Equivalently, if they're asking about 60 degrees, here's our 60. Again, same technique. We just make an equilateral triangle. So that's 1, that's 1, that's 1. That makes that 1/2. And then you use Pythagorean theorem to find the other part. So 30, 60, 90, 45-degree angles can actually be found with geometry, the sine and the cosine of these. One extremely useful theorem that comes about with sines and cosines is the theorem, the Pythagorean identity. It states that cosine squared theta plus sine squared theta equals 1. It's easiest to see on a unit circle, but it actually works for all size circles. For any angle, we have this theta written here. We've seen this picture once before already in this section. Cosine and sine. Pythagorean theorem, we have x squared plus y squared equals r squared. For this picture right here, that's x, that's y. That's really x right there, and that's y right there. And 1 is the radius. If we plug that in, x would be cosine, so x squared would be cosine squared, written right here, plus y squared, that would be sine squared, equals r squared, but r is 1, so that would be 1. So this is just the Pythagorean theorem written in terms of cosine and sine. Notice here, and this is a big thing to notice, cosine theta, that's a weird looking theta, there we go. That is what we really are working with when you see this expression. So this squared notation, sine squared, cosine squared, theta, is a shorthand notation for it's actually cosine theta squared. So when you see that, make sure that you're working out cosine theta and then squaring that value. Great. Another very important theorem is the reference angle theorem. So if you have alpha is an angle, it's the reference angle for theta. So here we have an example. Here's theta. Theta is 5 pi sixths. And alpha would be this pi sixth reference angle. It turns out that the sine 1/2 and the sine 1/2 of the reference angle are the same. The cosine, square root of 3 over 2, and the cosine minus square root of 3 over 2 only differ by a plus or a minus. So when you have these reference angles, cosine of theta will be plus or minus cosine of its reference angle, and sine theta will be plus or minus the sine of its reference angle. And that depends on which quadrant you're in. A nice thing about the quadrants, we have all students take calculus. This tells you that we don't even know what this is yet. This is tangent. We'll get to there. All, for now, sine and cosine are positive in quadrant 1. If your angle is in quadrant 2, like 5 pi 6, sine is positive, cosine is negative. In the fourth quadrant, cosine is positive, sine is negative. That helps you determine which of the plus minus this is. You'll see examples in other videos. The reference angle, if your angle is in quadrant 1, the reference angle is measured in this way. If it's in quadrant 2, the reference angle is measured off of the x-axis. For quadrant 3 angles, again, the reference angle is measured off of the x-axis. In quadrant 4, it's measured off of the x-axis. So make sure you're always measuring your reference angle off of the x-axis, never off of the y-axis. This is a list of the common cosine and sine values, the 0, 30, 45, 60, 90, also in radians. And there's a lot of patterns to help memorize this. And one way or the other, you want to have this stuff memorized. This is a view of the unit circle. This gives you sine and cosine for all the values all the way around. But notice, if we look at this value and its reference angle, there, there, there. All of these will be similar as far as the sine and cosine will be only plus or minus difference. And it's an easy way to find out which one's plus or minus. This point in the second quadrant is left, so the x value is negative. Then it's up, right? Y value is positive. This one is to the right and down, so x is positive, y is negative. So you can really only have to memorize the first ones and then use reference angles and quadrants to figure out the rest. You will be solving some equations in this section. For example, solve for all angles. Cosine equals 1/2. Cosine equals 1/2 at pi thirds, but also at 5 pi thirds, because cosine's positive in the first and the fourth quadrant. Now pi thirds, if you add what's 2 pi k, that will continue to add a full circle and continue to get you more and more and more of these angles. There's an infinite number of solutions to this equation. Same with 5 pi thirds. If you add 2k pi, you'll continue to find more and more solutions. You have to specify that integers k. K can be -2, -1, 0, 1, 2, etc. When you move beyond the unit circle, the points aren't just cosine sine anymore. Now it turns out that there are cosine for the x value and r sine for the y value. So x equals r cosine theta and y equals r sine theta. And cosine theta is then therefore x over r, and sine theta is y over r. So cosine is still related to x, but you have to divide by r to get the cosine. Or said another way, x is still related to cosine, but x is now equal to r cosine, where it used to just be cosine because r was 1. When you start to treat the point on the edge of a circle as an actual motion and you're following it around like the hand on a clock, then you get into the equations of motion. And they are, the x value would be r cosine omega t, where omega is the angular frequency, usually radians per minute or something like that going around, and y is r sine omega t. When you pass into functions like this, x equals a function, y equals a function of time, then you start to look at cosine and sine as functions. And as functions, the domain of both cosine and sine are negative infinity to positive infinity. You can plug anything you want into there. And the range is between negative 1 and positive 1, meaning you will never have anything larger than 1 come out of a sine function. These are useful in the future. Finally, when you have a triangle, here is theta, and you want to represent, we have A, B, and C for the sides. Cosine theta is A over C. Sine theta is B over C. It's a really nice thing to remember here. It's called SOH, so, CAH, Ka, and TOA, SOHCAHTOA. Now the T is for tangent. This is not in this section yet, but this comes in one package, SOHCAHTOA. This tells us that cosine is adjacent over hypotenuse. So here's theta. Cosine is adjacent A over hypotenuse, the longest, C. That's this formula. And sine of this angle would be opposite over hypotenuse, opposite hypotenuse. And that gives you these relationships in a much more convenient fashion. That completes the overview of this section.